Hi, class. Welcome back to the next section of chapter 13. Today we are going to discuss chapter 13.2, which is series. So, before we get into it, series is basically just a sequence where you are adding up all of the terms. So, let's look at a more formal definition. Again, we've seen the summation notation tons and tons and tons of times, so this should be somewhat of a review. Although there is lots of new stuff in this section as well, because we are talking about different aspects of series here. So for a definition, let's say we're given a series, right? It's defined by a sequence, AN, where we are adding all the terms of that sequence where it starts at n equals 1 and it goes on forever and ever to infinity. The way that this would look would be A1, our term A1, plus our term A2 defined by this sequence a sub n plus a3 plus a4 plus yada 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 all the way to n and then some, right? All the way until forever. We call capital S subscript n, S of n, the nth partial sum. So if I'm looking at S4, I would add up the first four terms, right? So the nth partial sum is the sum of the first n terms, is how I'll refer to this from now on. S sub n is the sum of whatever the n terms. So the sum of the n terms, first n terms, uh, will look like this, right? So the difference is my subscript here is n. Here, my subscript is I. Okay. K would have worked, anything would have worked, really. But I is pretty typical. And I'm going to stop at n because I'm adding up the first n terms, right? Here, however, I'm adding up to infinity. I'm not going to stop adding. I'm going to continue to add forever. So a partial sum might only add the first n terms together. So that would be n a1 plus a2 plus a3, so forth and so forth, up until whatever I designate the nth term to be. Okay. If the sequence of the sums, okay, so the sequence of n is me looking at 1 and then 1 plus 2 and then a1 plus a2 plus a3 and then a1 plus a2 plus a3 plus a4. So each term in this partial sum sequence here is me just adding up the terms from 1, 2, 3, 4, et cetera, for each term that I'm on, up to the term that I'm on, I should say. Okay, and if this sequence of partial sums is convergent and the limit of my partial sums as I go to infinity equals what I'll call here small s exists, such that this is a real number, um, then my series is called convergent. Okay? And we write that the sum of all of my terms equals little s can be also written as the sum of my sequence equals s. Okay? Basically, it's saying that if I add all these things up and it doesn't go to infinity, it goes to a value, a real number, then it converges to that value. Very similar to what we are talking about for sequences, where we look at each individual term and what the individual terms are doing. Here we're looking at what the sum of these terms are doing, right? Do they add up and just get bigger and bigger and bigger? Do they alternate? Do they stay constant? Do they converge to a value? Okay, that's what we're interested in for chapter 13. Okay. S is called the sum of the series. The little s is the sum of the series. If the sum of these values does not converge, then it's divergent. Okay, so if the sequence of terms of this partial sum diverges, it doesn't get closer and closer to some value, then our series itself is called divergent. Okay, so as a note, the sequence of partial sums starts off with just the first term. The next term in the sequence is the first and second term added together. Okay. The third one is the first three terms and so forth until I add up all of the terms up to n. And now this sequence of values, if this sequence converges, then my series as a whole converges. If this sequence diverges, then my series as a whole diverges. Okay, so that's the relationship between our sums and their partial sums. Okay, and their sequence terms. Therefore, the sum of my sequence, so my series is what I'll call it from now on. So my series from 1 to infinity is equal to the limit of the sum of my series of partial sums, right? Here I'm going from I is 1 to n, right? So I'm gonna let these partial sums get larger and larger and larger in value, right? My n is gonna go to infinity here. So it'll start off low, and then I'll just start adding up more and more terms, right? Um, so that's the equality, okay? The series is equal to the limit of the partial sums, okay? So as we said here before, very important to remember. The sum of a series is the limit of the sequence of partial sums. So that's just me writing out what this means mathematically, right? So this mathematical relationship is basically that the sum of the series is the limit of the sequence of partial sums. Okay. So let's look at some special sums, right? Here we have a to the r to the n minus 1 term. Okay, we looked at this, something very similar to this in the last section in sequences. So we'll kind of pull those together at some point. I'm not sure if we do that here or in a later section. But this, if I plug in 1, the first term here goes to 0, and I'm left with just a. When I plug in 2, I'll get a times r, right? Because 2 minus 1 is 1. When I have 3, I'll be r squared, r cubed, r fourth, r fifth, so forth and so forth, until I reach my term, and then I continue to go. So again, this is just the generalized form, just me being nice when I write it here. It goes to infinity, which is why you see these dots to continue to go. Okay. I cannot let a be 0, because if a is 0, then I'm just adding up a bunch of zeros, and my sum is 0. Okay. And that's nice, and it converges and everything, but it's not interesting. So this series here is called the geometric series. So if you did go and look through my pre-calculus stuff, I believe we talked about this quite a bit, and that kind of glazed over the pre-calculus sort of information. And we're gonna go into our deep dive of geometric series. Not deep dive, but deeper. So let's note that the partial sum for the geometric series would be a plus ar plus ar squared all the way up to this nth term. This would be my nth term, right? Because for 1, I start here, right? I'm always 1 less. So there would be 1, 2, 3, da, 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 up to n. So this would be the nth term. So the nth part, first, the sum of the first n part terms looks like this. Okay. Now if I multiply my previous result, right, my first n sums by r, then it looks like this, right? Then my last term, instead of my last term being arn minus 1, my last term would be ar to the n. Instead of my first term being a, it would be ar. And every value of r, every power increases by 1 because I'm multiplying it by r. If I subtract those two results, me taking the partial sum of n and r times the n partial sums, that formula will look like this first one minus the second one. Okay, so I have my n partial sum minus my r times the first n partial sums. And if we simplify this, you see that a doesn't have a common term to subtract, but ar subtracts the first term and r times Sn. Ar squared on the second, ar cubed on the last one. The last term of um, the first n partial sums, arn minus 1, and that cancels out with the second to last. So the only thing that's left is the first term from the first n partial sum and the last term from r times the first n partial sums. So that leaves me with the difference of the partial sum and r times the n partial terms is a minus a r to the n. Okay. So if I factor out the common terms here the first n partial sum symbol, here factoring out a, I can now isolate the first n partial sums and have the formula a times 1 minus r to the n over 1 minus r. So what this gives me now is a closed form formula for the first n partial sums for a geometric series. Okay, so this is very useful. So let's recall some information about our geometric series. We looked at the sequence, the geometric sequence in the last video. So the limit as n goes to infinity of r to the n is 0 if I'm in between -1 and 1, because remember it's less than small values will continue to get small as I take their powers. If I am equal to 1, then my limit is just equal to 1. Okay. I cannot be -1 and I cannot be larger than 1 or less than -1. So these are the only two values that my limit is allowed to be. It goes to infinity, it diverges for every other value of r possible. Okay, so I have to be either 1 or in between -1 and 1. And these are the values of the limit for those cases. Okay, so that's nice now because now I have a closed form formula for the first n partial sums, and I can talk about whether or not this sequence, if I keep taking large and larger and larger values, whether or not it converges or diverges, right? So my series for a geometric series is equal to the limit of the first n partial sums as I let n get very, very large, which is going to be equal to the limit as n goes to infinity of a times 1 minus r to the n divided by 1 minus r. So now, based on what my r is, I can talk about what my geometric sum is. All right. Therefore, if r is between -1 and 1, I'm just going to get 0 out, right? This numerator, I'm sorry, not 0. I'm going to get a um, over 1 minus r because r to the n is going to go to 0. This denominator does not have an n on it. So this 1 minus r to the n will turn into just 1, and this 1 minus r stays the same. So my partial sum then would be a over 1 minus r for a geometric series if my r value is between -1 and 1. If my r is equal to 1, then this function is 0, right? This would still be, well, this would be 1 minus 1, so that would be 0, but really this is what I'm looking at because this is going to, this is what's happening for my limit, this r to the n. So this would still be 1 minus r. This would be 0 on top, and the limit of 0 is 0. Okay. And it's divergent for all other values because for any other value, the r to the n diverges. So therefore, my sum for the geometric series, okay, is going to be a over 1 minus r if r is between -1 and 1. It's going to be 0 if r is equal to 1, and divergent for any other value of r in a geometric series. Okay, so let's look at an example. Let's consider the formula 4 plus 3 plus 9 over 4 plus 27 over 16, so forth and so forth and so forth. So let's try to figure out what's going on here. Okay, so if this is geometric, the first value is just a, and the second value is a times r. The next one is a squared, and so forth and so forth. Okay, so here, if this is geometric, this would be a. Okay, if this is geometric, this is a times r. So this would be a would be 4, a times r would be 4 times some number equals 3, and then I can solve for that and so forth and so forth. So we can see what's happening here. This is squaring, right? It looks like maybe I have a 3 squared. This would be like 3 to the first power, 3 squared, 3 cubed, and here this would be 3, 0. Okay, it would just be 1. And I would leave you with 4. On the denominator, it looks like I possibly have a 2 in the denominator, right? If this is 9, 3 squared, and 2 squared, 3 cubed, 2 cubed, right? Here would have just been uh, 3 to the first power, 2 to the first power, and this 4. So let's kind of write some stuff down. So we want to find the 10th partial sum and the sum of the series completely. So again, we're going to notice that the sum is geometric with A equals to 4 and A times R is equal to 3, okay, which implies that 4 times R is equal to 3 because A is 4, A times R is the second term, which is 3. So solving for 3, we have R is 3/4, okay. So my first 10 terms would be, um, oops, okay. So we're not doing the series here, okay. We are doing the formula for the first 10 partial sums. So in this case, my A is 4, my R was 3/4, and my N is 10 because I'm trying to find my 10th partial sum. So this is the formula we're using, okay, just so that we're very clear here. Right? A 1 minus R to the N over 1 minus R. Okay, so 4 is my A term. 1 minus R, I just found here that R was 3/4. I'm finding the 10th partial sum, so that's 10. So then I would do the math here, right? 1 minus 3/4 is 1/4. I have no idea what 3 to the 10th is, 4 to the 10th is, so I can either do the math around this or I can plug this into my calculator. Calculator is probably the easiest way to go. So my 10th partial sum is 15 point and a bunch of stuff, right? So this is what, 1, 2, 3. So 10 decimals, 11 decimals, 1, 2, 3, 4, 6, 7, 8, 9, 10. So 10 decimal places of accuracy, okay? And my total sum, right, of if I let this go to infinity, is going to be follow this formula. So my R is 3/4, so that's in between -1 and 1. So I'll use this formula to calculate the complete sum. So I know A is 4, so it'll be 4 over 1 minus 3/4. Okay. 1 minus 3/4 is 1/4, right? And then this equals 16, which, hey, look, I'm not at 16, but I'm fairly close to 16 for adding up 10 terms, right? So if I add up terms for an infinite amount of time, I will have a value of 16. Okay, so as I continue to add more and more and more terms, I approach a value of 16, but in this case, this is an upper bound. It does not go past 16. I will never be larger than 16. And I'm only going to be equal to 16 if I add an infinite number of terms. Okay, so let's give a quick definition. So again, we're actually kind of looking at some special sums. So the first special sum was the geometric series. Okay. The next one is telescoping sums. We actually use an example of telescoping sums to derive our formula for the geometric series for all of those formulas that we have for it. A telescoping sum, right? Telescopic sum is a sum where the terms cancel in pairs, leaving only two terms. So we did that when we derived the formula here for Sn, where I neatly took the nth partial sum and I multiplied it times r, and then I subtracted it. And when we did that, everything fell out except for the first term and the last term, and that's how I found my formula. So telescoping sum um, is just that, right? Something where everything disappears except for the first term and the last term, right? Everything cancels out in pairs. So we use this in order to find the sum of the geometric series above. Okay. The next important series is the harmonic series. Okay, the harmonic series is a series that's just 1 over n. Okay, so we would start off at 1, right? 1 over 1 is 1, and then 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, 1/8, 1/9, 1/10, etc., etc. Okay, and we're just gonna add all of those things together. So that is the harmonic series. This is a very important series as well, which we will study more in depth. I'm not really sure if we're doing that later in this section or later in this chapter. We definitely do it later in the chapter, but we might study it some more here as well. Okay, so let's look at our next theorem. If the series is convergent, then the limit of the sequence of terms goes to zero. Okay. It is very important that you do not switch this around. Okay. So my series converges. If I add everything up, it'll add up to some value. Okay. If that's true, then the limit of the sequences go to zero. So for instance, for the previous one, um, right here, the limit of, if I were to write this in a general form, right, it would look like 4 times 3 to the fourth to the n minus 1, because again, it's a geometric series, right? I can write it in this form. So my a was 4, r was 3/4, n minus 1 was the power. If I were to look at that and take its limit of that general term, that would go to 0, right? So 4 times 3 to the fourth, right, n minus 1, that would continue to get smaller and smaller and smaller as um, as I look at the limit here, right? 4 times 3/4 n minus 1. If I took that limit, its limit will go to 0, okay? And that's because I know it's convergent. I cannot look at my function or my series, my general term, take its limit and say, hey, that limit goes to 0. That means this is convergent. That is not true, okay? The limit goes to 0. So if it's convergent, then its term will go to 0. The converse of this is not true. The converse means that if I'm looking at the limit of the sequence and it goes to 0, yeah, then it's convergent. No, false. Okay, do not do that. It's a very common mistake that students make, and it leads you in a lot of trouble, right? You'll start getting a lot of stuff wrong, and you're like, "How come this stuff doesn't make sense?" It's because you're doing it wrong, right? So, you cannot look at the limit in this way to talk about the series. Okay, there are things that we can do with limits, but that's not one of them. So the converse is not true. So let's look at an example. You cannot, cannot determine convergence if the limit of the sequence is 0. The limit of the sequence of terms going to 0 has nothing to do with the convergence, but the convergence does have something to do with the sequence, right? Using this fact, I can talk about this, but I cannot use this fact to talk about that, okay? So let's look at an example for why this is true. Let's consider the harmonic sequence, the harmonic series, this 1 over n that we're talking about, okay? The limit as n goes to infinity of 1 over n is 0, but the harmonic series is a divergent series, right? So yeah, the sequence of 1 over n, it does go to 0, but the series, the sum of all of those things, does not go to 0, right? So again, I'm reiterating this a lot because it's very important. I cannot talk about the limit in order to determine convergence. But if I have convergence, I can talk about the limit, right? So I can talk about 1, but it doesn't go both ways. It only goes in one direction. That's the important thing I'm trying to stress here, right? We do have several ways for determining whether or not a series converges or diverges, and that is exactly what we're interested in for chapter 13, right? Pretty much all of this chapter focuses on convergence and divergence. That's really, we have 11 sections in here. One is on sequences. I want to say the next 6 or 7 is all about divergence or convergence, and then we kind of put it all together for some other stuff later. Okay. Test for divergence. If the limit of the sequence of terms as n goes to infinity does not exist, or if it doesn't go to 0, okay, so does not exist means that it would have to have a 0 in the denominator, or, well, no, actually, it's a limit, so that doesn't matter. It would have to go to infinity or negative infinity, or not 0. Okay, so if that's true, then the series is divergent. However, if it does go to 0, I cannot say that it is convergent, as I said before. But if the limit does not go to 0, I can determine divergence by looking at the limit, right? Divergence, I can tell. Convergence, I cannot tell by looking at the limit. Okay, so theorem. If the series of the terms for A and the series of terms of B are convergent series, then they follow a few rules, um, such as the series C times A also being convergent, and the sum of two convergent series are convergent, and the difference of two convergent series is convergent. Then the following is also true, right? The sum of C, a constant times all of the terms of my sequence, is the same as a constant times the sum of the sequence. Okay. A plus or minus B, term by term, is the same as taking those separate sequences and subtracting or adding their sums. Okay. So example 2. We want to determine whether the series is convergent or divergent. If it's convergent, we want to find the sum. All right, so for the first one, we have the sequence 1 over 3, 2 over 9, 1 over 27, 2 over 81, 1 over 243, 2 over 729. So if this is geometric, super nice, and we have a way to determine always, okay? If it's not geometric, we'd have to kind of determine if it's one of the other special sums that we have. Really just a harmonic is the only one that we have, and we could tell it doesn't look like it's harmonic. And so let's just try to find a general term, okay? So you can see here I have 1 over 3, 2 over 9, 1 over 27, 2 over 81, 1 over 243, 2 over 729. So the first thing that I notice is that the denominator continues to get larger. It looks like it's going up by um, powers of 3, right? 3 times 3 times 3 times 3 times 3 times 3. So this is 3 to the 0 power, or I'm sorry, 3 to the 1 power squared, right? Cubed, fourth, whatever. Um, the numerator is oscillating between 1 and 2. I have no idea how to make a numerator change between a value that is not 1 and -1. Um, the only way that I could see to do this would have something like taking the middle value, which is 0.5 or 1.5, and no, right? I can't do this. I can't add this. I can't add one, minus one, add one, minus one. The most I would be able to do is oscillate by a value of 2. Okay. So what I would want to do here, since I can find a value for the denominator, something that would work, right? It looks like n, 3 to the n is what I would have on the denominator. The numerator I can't find anything for. So using what we've been talking about up here, looks like the easiest thing for me to do is to kind of look at it in terms of like maybe two different series, okay? Where one has 1 in the numerator and the other has 2 in the numerator. And then I just got to figure out what to do with my denominator, how I'm going to split those apart, right? So let's go ahead and split these, all the ones together and all the twos together, okay? And then it's a little bit easier to let me see what's going on. So this is 3 to the power of 1. And then this is 3 cubed, right? So, so 1 squared, so this would be cubed, fourth, so this would be fifth. So this looks like the power is going up by an odd number. Each time it's going up by 2, but an odd number. This is going up by 2, but an even number, because this is 3 squared, 3 fourth, 3 to the 6th, so forth. Okay, so I just need to write that down in terms of what I have. So for the first one, I would write this as 1/3, okay? And I could write it as 2n minus 1. Um, but then if I simplify that and pull it out, I should be able to simplify this to 1 over 9 to the n minus 1. It's better to write it like this than 1 over 3 to the power of 2n minus 1. So I'm counting by odd powers because here this is geometric in form. I have uh, a single term, an a, and then I have an r that is to the power of n minus 1. And I'm going to do the same thing over here. So remember what we said in the last video? Sequences can be written a multitude of different ways. So if I know a lot about geometric series, I would want to write this in terms something that would help me as a geometric. So this helps a lot more, right? So my first term here is 2 to the ninth, but it increases, the denominator here increases in the same way that this does. So again, this is still pretty much right, 3 squared to the 2n minus 1. And so I'm still counting kind of in odd numbers here. And so knowing this, I can now determine whether it's convergent or divergent and look at its sums. If it does converge, because it's geometric in form, right? So here my R for both of these is 1/9, right? 1 over 9. That's in between -1 and 1. So that's the condition I need for it to converge. So both of these converge, and then I should be able to calculate the formulas for this now, right? Since they converge, it's A over 1 minus R, and I add those together. A over 1 minus R. So I just do the math, right? So this is 1/3, this is 8 over 9, this is 8 over 9, and then when I flip these over, I get this way. Those nines will cancel, so this will be 5/8. This one, uh, which simplifies to 5/8. Okay, so I added this together so that I had a common denominator is already common, but I can turn this into 3 over 9, and then 3 plus 5, 3 plus 2 is 5 on top with a 9 on the bottom, right? And this is 8 over 9, 8 over 9, so it's already a common denominator of 8 over 9. So when I simplify this, it simplifies to 5 over 8. So I split these into two different geometric sums, okay? So I took one sequence and I split it into two, and I found the sum of both of them individually since they were geometric in nature, and I added them together. Okay. Here, instead of starting with our sequence, we're giving our general form, okay? And so from here, let's see if we can pull this apart in some way, or if we can just look at it and say, oh, yes, it's geometric. If it's not geometric, maybe I use one of these formulas that I have about series, okay, as I did in the previous one. So here, uh, we can just look at the term. This term diverges, okay? This is 2 to the thirds to the n, so as n gets really, really large, this right here goes to 0, and I'm left with 1 over 1. And remember what my test for divergence says. If the limit does not exist, or if the limit is not 0, then my series diverges. So my series here does not pass or it fails, I should say, the divergence test, passes the divergence test. So it's divergent. Okay. So here again, the reason is 1 over 1 plus 0 is 1, which is not equal to 0. So let's do another example. So it's asking us to write the sum starting at n equals 2 of 2 over n squared minus 1 as a telescoping sum, and to find the sum if it converges. Now, for telescoping sum, if I want to write something as a telescoping sum, there's really kind of a condition I need, and not always, but it helps, is if I can deconstruct this ratio using partial fraction decomposition. So if I can use partial fraction decomposition, generally I can change this into some sort of a telescoping sum. So that's what we're going to do. We're going to look at this and we're going to factor the denominator, try to pull this apart into a sum or difference of two different series. Okay, so I'll go ahead and factor the denominator using partial fraction decomposition. Um, I have a over n plus 1 plus b over n minus 1. Okay. Clear my denominators, and I'm left with 2. A gets multiplied times the only denominator it doesn't have, which is the n minus 1. B gets multiplied by the denominator it doesn't have, which is n plus 1, and everything else gets canceled out. Okay, if you don't remember how to do this, you should go review. Here I'm going to solve for everything. So I'm going to get 2 is a times n minus a plus bn plus b. Okay, that's equal to 2. I am going to combine all my like terms. So an plus bn is going to equal 0 because there's no n's on the left-hand side. B minus A is going to equal 2 because those are my constants. So my constants have to equal and my n terms have to equal. So I get A plus B equals 0 from the n terms. B minus A is 2 from the others. So from here, it's a system of two equations with two unknowns. I can solve it. So I have A equals negative B, okay, which you can see from here straight away. Therefore, from this first term, since A is equal to B, I can write this as B minus a negative B. So that's 2B is 2. So then B is equal to 1, which means that A is the opposite value of that, which is negative 1. So my series then can be rewritten as partial fraction decomposition, 1 over n minus 1 minus 1 over n plus 1. We know that I can distribute this sum across here, okay? And before we do that, um, let's go ahead and just write it term by term. So even if I had distribute this across, if I wrote it term by term, I would have wrote one out and then the other out. But let's write this series out one term at a time. So again, we're starting at n equals 2. So I have 1 over 1 minus 1. Again, I can't even start at n equals 1 because I would have an undefined term in the bottom. So I have to start at n equals 2 for this series. Plugging in 2, I get 1 over 1. This is 1 over 1/3. Then I plug in n equals 3. Then I'll plug in n equals 4 and n equals 5 and so forth and so forth. I just need a few terms so I can see what's happening. And let's look at what we have from our sum, right? So if I was doing this on my own, which I did, right, I would just plug stuff in and see what I get out of my numbers, okay? Here, notice that this 1, there's no other ones. This 1/3, there's a positive, okay? This 1/2, I don't see any other 1/2s. This negative 1/4, there's a positive 1/4, okay? This negative 1/5, will I have a 1/5? Yes, on the next one I would have a 1/5. So a lot of stuff cancels out, and it looks like this 1 and this 1/2 remain, and everything else cancels with something, or will cancel with something, okay? So here, I'll go ahead and separate the two halves, all the positives and all the negatives, so that we can see what's happening a little bit clear. So here, 1/2, 1/3, 1/4, and just as I said before, starting at 1/3 and on, everything kind of cancels. And so then we're left with 1 plus 1/2 as our sum, which is 3/2. So this series here is not geometric at all, okay? So I wouldn't be able to find what it converges to by using geometric series stuff. Okay. In fact, I would have been stuck if I didn't know, hey, use partial fractions. Right. So using partial fractions, I can decompose it into a difference of two different series, which then does telescope, which leaves me with two numbers left over, which I can add together, which gets me its sum. So I'm able to take this and say, oh, I know what this converges to. It's 1.5. Let's do one more example. So let's express 0.46 repeating. So, I don't know how to make this bar larger. Normally, I'm pretty good at the stuff I do on the program I use to write this, but I could not get this to go over both numbers. Um, Regardless, 0.46 repeating is just 0.46, 46, 46, 46, so forth and so forth and so forth. So if we want to write this as a ratio of integers, I need to break it into pieces, okay? And I want to write it as a series. And so the first part of that is that I take the first two terms that are together, and I notice that this 0.46 is in the hundreds place. So if I want to write this as a fraction, it would be 46 over 100. The next 46 it ends in so this is 10, hundreds, this is thousands, this is 10,000. So this would be 46 over 10,000 and so forth and so forth. And I can then add them together, right? So this is 46 times 10 in the second place, or 100. The next 46 ends in the fourth decimal place, so I can put that over 10 to the fourth, or 10,000. The next one is in the sixth, so forth and so forth, okay? So if I look at this sequence, right, I have a 46 over 10. It looks very geometric to me. The numerator stays the same, okay, but the denominator is increasing by a power each time. So 46 over 100, 46 over 100 squared, 46 over 1,000, right? If I simplify this a little bit, okay, so I can write this as the first term, 46 over 100. That means that the second term is A times R. So there's two 100s, so 46 over 100. The second one comes over 1 over 100. And every time I increase in power, um, I am increasing by 1. So that was kind of the problem here, that I was increasing by 2. Now that I'm increasing by 1, I can write this as a sequence. So when this is 1, 1 minus 1 is 0, and I'm left with 46 over 100. The next count up, which is 2, I have 46 over 100 times 1 over 100, so that's the 100 squared. And then another 100 and another 100, and so forth and so forth. So now that this is geometric in form, I have a form for my sequence, a rule for my sequence. 1 over 100 is my R. 46 over 100 is my A. This is in between -1 and 1. So that means that this converges, and I can figure out what the sum converges to. So it's A over 1 minus R. So this is going to be 99 over 100, right? 1 minus 1 over 100. So I have 46 over 100 divided by 99 over 100. Those hundreds cancel, especially when I flip and multiply the bottom denominator, and I get 46 over 99, which does not simplify because this is multiples of 3, and these are all evens. And when I cut this in half, it's 23, which is prime. So 46 over 99 is as small as it can go. And that is our discussion on series. Okay, so in the next video, 13.3, we will start talking more about how to determine convergence. And that's what we'll do for the next few chapters is different methods of convergence. Okay. All right. See you guys on the next one.